Our next speaker is Lucas Verga. He is also a postdoc at IQSC.
So good morning, everyone. Thank you, Jonathan, for the introduction. My name is Lucas. I'm a postdoc here in the group of Professor Juarez. And today I'm going to give you a little overview of what's going on about CO2 reduction in the group, especially on transition metal nanoparticles, defected surfaces, and some perspectives of what we intend to do in the future. So before starting, I would like to acknowledge to thank everyone in the CO2 team and the agencies and institutions that allow this work to happen, because some of these data they are not mine, so I need to thank especially for Paulo and Viviane that are doing lots of the work here. So why we are studying CO2 reduction to value-added products? Basically, CO2 reduction can work as a route for sustainability. So in our transition to a sustainable society, in many ways. So the first way, it helps to store this excess energy produced from renewable sources. Secondly, and I think this is quite interesting, it can generate products that are commonly obtained from fossil fuels. So it's not just a way of storing energy like a battery, but can also produce things that are usually obtained from these fossil sources. And thirdly, it can help with the recycling of CO2. So these are quite interesting things to happen for this sustainable change. But we have a big problem here, which is optimizing catalysts for this reaction, because these catalysts need to be active and selected to make this process viable for like a long goal. And when you're thinking about optimizing a catalyst, you have a big problem because this is a multivariable problem and lots of these variables are interconnected. So using, as an example, just a supported nanoparticle for an electrocatalytic system. We could control, for example, the nanoparticle composition, size, morphology, and decide to alloy this nanoparticle. Each one of these things could change the activity of the catalyst. We could also change the support, composition, and the phase that the facet that you're allowing this interaction to happen. And we can change the electrolyte. Each one of these variables can change the activity. And also, if you change one of these variables, for example, the nanoparticle size, you indirectly affect the morphology and the interaction nanoparticle support. So you have an additional effect, an interplay of effects. So when you have all of these variables, obtaining an atomistic understanding of those characteristics is quite important to design better catalysts. So how we are trying to tackle this inside the group? We are attacking in three different fronts. So first, we are trying to understand the CO2 activation. And when I mean activation, is not just if the molecule chemsorbs on the surface and bend, but also how is the preferred configuration. Because depending on how this molecule adsorbs, we can favor a route to forming like CO, methanol, or formic acid, for example. So it's quite important to understand that. We are also studying the adsorption of key intermediates of the reactions to get like a quite thermodynamic view of the reaction mechanisms. And we are properly starting to study reaction mechanisms, both in a thermodynamic way or like a kinetic way for some reaction steps. We are doing that mainly with DFT, using VASP and FHI aims, with appropriate algorithms for each one of the cases we want to study, and using some scripts and codes that are built inside the group. The idea is doing all of that in different materials, ranging from like nanoclusters to alloys, and some more complex materials like nano interfaces of metal oxides and transition metal clusters and things like that. So, okay, one of the effects we are studying in the group are nanoparticle size effects, And why we are studying that? Because when you change the nanoparticle size, you change the way the nanoparticle surface interacts with reactants or intermediates. And this affects the activity and selectivity of your catalyst. It's important here to stress that we have two regimes when we are talking about nanoparticle size effects. We have a scalable regime, so where we study things, which we see the changes, and we can like predict things from larger nanoparticles and things like that. And we have a non-scalable regime, usually for nanoparticles, or in this case, nanoclusters, with like diameter smaller than 1 nanometer, depending on the material, depending on the metal, where we have the so-called every atom counts regime. So for example, here we have copper 3 is the green line, and copper 4 is the blue line. And these are the basically the activity of the catalyst for methanol production. Okay, so the first thing is trying to understand what are the sources of these size effects. So we have some like quite intuitive things. When you change the nanoparticle size, if you decrease the nanoparticle size, you increase the surface area per volume ratio. But you also have some non-trivial effects, like you can change the nanoparticle morphology. Some of them will be preferred depending on the size. You can change the ratio between different types of sites. So this is an example of this effect. This is what we see for these types of surface atoms. And this is the corner and edges atoms. So if you have a large nanoparticle, most of your surface atoms will be terrace-like atoms. If you have a really small nanoparticles, you have lots of edges and corners, and the activity of them should be different. Also, you can induce some bond length strengths, and you can have quantum effects and interplay with other variables, like I said before, which are a bit more like tricky and quite special, especially important for the non-scalable regime. Oops. Okay. So one of the studies we did here about that is studying the adsorption of CO2, CO, water, and hydrogen on different sizes of nanoparticles or nanoclusters from 13 to 147 and an extended surface for 3D metals. Basically, we calculated adsorption and interaction energies and observed that in general, when we decrease the size of the nanoparticle, we increase the interaction strength, basically. But these strengths, they are not that smooth. They can be different depending on the metal and depending on the adsorbate, especially because for these two cases here, 1355, we are in that non-scalable regime where things can be a bit trickier. For CO2, that was what's more like what is the molecule that we are most interested about. We see that cobalt and nickel, we observe an adsorption strength when we decrease the nanoparticle size. While for copper, the values are almost the same for all the cases. And the physisorbed state is the preferred one for everything. However, if we go a bit deeper in these results about copper, we observe that the distance between CO2 and copper decreases as we decrease the nanoparticle size. And for clusters with 55 and 13 atoms, a bent CO2 can be observed as a higher energy configuration. So it is possible to activate CO2 due to size effects on copper. These results are here in this paper that we are about to submit. So you're welcome to check a little bit more about that. But now, if we are interested to go to larger nanoparticles, when we think about doing like 309 atoms or something like that, the computational cost will become quite unfeasible. So we need to find a different strategy. So one way we are planning to do that is using surfaces with different types of defects to mimic the surface of a nanoparticle. However, to do that, we also need a kind of descriptor that we can encode these results and transport what we find to nanoparticles. So we are planning to use the generalized coordination number, which is basically a normal coordination number as everyone like know from chemistry. But instead of counting just the first neighbors, I weight each neighbor based on their own coordination. So I count the coordination of my first neighbors and use that to assess like their weight to the generalized coordination number. This number was first tested for oxygen reduction reactions and has been recently found to be good for CO2 reduction on copper catalysts. This is just an example of the generalized coordination numbers for different nanoparticle sizes and shapes. And if you see, if I use just a stepped surface like a 5331, I can get some of these effects, like I can get a white ones and then just the blue ones, so these things here, but I can't get vertex and edges properly described. So I need to include defects and like trimers or things like that in the surface to decrease the coordination. So these are quite fresh results. The first thing we were trying to see is if we can mimic the behavior of copper with the nanoparticle size. So like I said before, for copper, CO2 interacts mainly as a linear physisorbed molecule. But if I decrease the catalyst, the nanoparticle size, I can get CO2 activated as a higher energy configuration, especially for the edges and corners of the cluster. So really like low coordination sites. When we try to do the same thing on surfaces, the 533, I can't see bent CO2. I need to do those modifications, add defects and etc. to get low coordinated sites and obtain activated CO2. And I only get them if I have a really low coordinated site. So at least qualitatively, we get the same trend. Now we started studying adsorption of CO and COOH, which are intermediate for these reactions of CO2. And what we observed here, like all these plots here are all top sites except this one. And if we move from this one to this one, we are increasing the coordination of the site. And the adsorption energies increase. Well, yeah, they increase in value. So they are weaker as we go to more uncoordinated sites, which is similar to what we observed with the nanoparticle size decreasing and the adsorption strengths increasing. For COOH, we observe basically the same idea, and we can then also try to mimic different types of configurations. So CO adsorbing with like a parallel bond and DOH for the other side and so on. So this is good because, qualitatively, we can get some of the trends from the nanoparticle size effects. Of course, we won't be able to see quantum size effects and things like that, but still, because of the reduction in the computational cost, we will be able to do more complicated things like investigating a little bit more the reactions and etc. So with that, we will start doing two types of studies on reaction. This is what we intend to do in the future. One is the work I'm doing, so trying to get like a more thermodynamical view of the reactions. And the other one is using the NEB, for example, or something like that, a transition state search method, to get the activation barriers for some reaction steps. We also intend now to start studying the same things in different materials, not just transition metals. So we are doing a work with dechalcogenides, nanoflakes, and we are doping that with iron to see if the activation of CO2 will change, and also using some nano interfaces between metal oxide, this case here is zirconia, and a TMN to see what's going on, if the interface changes something or this is an important effect. All of that, because of all of that, especially because of the simplified models we are doing for the reactions, we will start collaborations with some experimentalists and see if we can mimic or explain some of the effects they are seeing in the lab. So to conclude here, we are tackling this problem of CO2 reduction in 3 fronts: CO2 activation, adsorption of intermediates, and study of reaction steps. And we will test different classes of materials. We have studied the size effect and observed that decreasing the size increases the interaction of CO2 with the surfaces for nickel and cobalt and allow activated CO2 to appear for copper catalysts, for copper nanoparticles. We also started to use copper surfaces with steps and defects, and we are being able to reproduce to a certain extent some of these effects that arise from the changing nanoparticle size and morphology. By doing that, we will be able to start studies about reaction mechanisms and some specific reaction steps that are important for the CO2 reactions. And we will use all this knowledge to extend that to a different set of materials to like deepen our understanding on this on this topic. So again, I would like to thank everyone from the group, all the institutions that are allowing this work to happen, and all of you for listening. Thank you.
We are now open for questions.
Hi. If you have no experimental data to compare with your simulations, how confident are you when you decided your DFT method and your basis set?
Yeah, well, that's a thing. One thing we need. Oh, sorry. One thing we need to do is finding things that are comparable to experiments. So, for example, these reduced systems that we are saying, like using surfaces and things like that, they will be able to give us some idea, for example, about the overpotential you need to activate to open a certain pathway to a reaction mechanism. So, if you have that, you can have at least an idea that your model is suitable or not. So this is just one example. For the reaction mechanism, for the reaction steps that we want to study, if we include that in some kind of, I don't know, microkinetic model or something like that, we can get, for example, the specific activity of the catalyst, basically. So we have some things that we can get to compare. Yeah, for now, like for my case, I have most like preliminary results. So, and also as a normal, like a standard, like let's say approach in DFT, we do lots of convergence calculations to know basis sets. So this is not a problem at all. And for the exchange correlation, we also can compare with the literature what's going on, like if they get similar conclusions for other reaction mechanisms and things like that to decide for our model. So these are two things that we can do, at least to ensure some comparability with experiments. But if we really want values that are comparable with experiments, then you need to find any macroscopic value that you can get from experiments.
We have more questions.
Thank you for the talk, very nice talk. And concerning you said that you were interested in looking at the thermodynamics of everything. And have you looked at the thermodynamics of the structural changes that may happen in your nanoparticles or your defects of what happens? And for instance, at CO2, do you take into considerations that maybe you have vibrations and angle bending and this kind of stuff? How
yeah, that's quite interesting. If we want to, for now, what I'm saying about thermodynamic picture is quite a crude picture, of course. But if we want to extend that for like making our our total energies calculations to become something more comparable, I would have to include that to transform that to a Gibbs free energy. So I would have to include like rotational, translational, vibrational frequencies, and do all the ab initio thermodynamics standard approach. So I'm not doing that now because this is our, like I said, like really fresh results, last week results. But if we want to extend that and have a better, let's say, picture of the mechanism, then we have to include these kind of things. And we have like standard ways to do it. So it's not a big problem. Okay.
Do we have more questions? Seems that's not the case, so let's thank the speaker once again.